Welcome guys, I am finally making an official video for the Debugger Buddy announcement. This is the version that I felt was good enough to make the version 1. Like I've said before, I felt like I just needed to put a baseline down and actually release what I thought was good enough for other people to follow along and build their own. I already do have some changes in mind that I'm going to make, but like I said, this is version 1. I've already made one revision to this document. It can be found on my website. I'll put the link in the description and on the screen. And you can download the entire build package. It has the Gerber files, the parts that you need, recommended default values, stuff like that. So I'm going to go through the description document here. So first we've got just the title page, has a picture of it. Contents, just have a little rev history here so you can see how it's changed over time. So this is just an introduction. You can pause it and read it if you want, but it's basically just talking about, you know, the basic capabilities of the board, which is 4 digital inputs, 4 analog inputs, how it does it, and that it says that it records it to an SD card as a text file, and you can just open that as a CSV and plot your data. So this is just describing the, actually I need to change this. This says 32U4. I need to change it to M0, but it's the same pinout for both of them. It's just a different controller. So analog components for the Debugger Buddy are housed under the microcontroller, and it is just a series of voltage dividers you can see right here, and you can configure those to be whatever you want. Okay, so for the analog components, we've got 100K on R1 and 60K on R2 for the first 3 dividers. This reduces a 5 volt reference voltage down to a 3.3 volt, and that lets you put it right into the analog pins on the microcontroller. I have done some research about this. I think I need to put in a voltage follower to isolate the input from the voltage divider. That's probably something I will do in the next version of this board. The 4th divider has a 100K and a 10K for R1 and 2 respectively, and that reduces a 30 volt limit or reference voltage down to a 3.3 volt. Here you can just see the diagram of the dividers. I still have 60K on there. Really, these values are all up to the user to put in what they are going to need for a reference voltage. So I did a 30 volt here because sometimes I will read the voltage that's going into like a DC controlled LED, like a COB LED or something like that. But basically this is all user configurable by changing these resistors right here. This is just the formula for voltage out from the voltage divider. And a problem I noticed is the 60K I think is too high to pull a reference voltage down to 0, or like to pull the pin down to 0. I think 60K is too high and it leaves it floating a little bit. So I'll probably reduce that whenever I update the reference board and I switch out the resistors IRL. I will update this document to reflect that. Okay, the digital components are a bit more complicated, but they're still pretty simple. Drill bit here. So it uses 2 LM393s. Those are just basically going to be trigger ICs, and you can set the reference voltage, which is done with R15 and R16, and that is setting the reference voltage in respect to the 3.3 volts. So the VCC on the board is 3.3 volts. A R1 of 100K and R2 of 60K drops it down to 1.2, and so that gives it a pretty good logic level threshold to switch between high and low. All these are just supporting components for the LM393, like stabilizing capacitors and pull up and pull down resistors. Here you can see a schematic of just how the LM393s are connected and the supporting components, like I said. Here's the threshold divider, which just tells you where you want that trigger point to be. So for logic level 3.3 volts or 5 volts, I thought 1.2 volts was pretty good, and I already was using a bunch of 1000 or 100k and 60k resistors, so it worked out pretty well. And you can swap that for whatever you want. It's literally just changing resistors, and I have right here marked R1 and R2 just for convenience. Okay, so power and charging components, that's going to be this guy, these dudes, and this header mostly. The J7 header is a little convoluted the way it's connected. I made it simple on the schematic, and if you hook it up just the way this little box right here shows, it'll all work. I was kind of trying to wrap my head around it because I built the board a while after I made the schematic, and I was trying to trace it in my head where the voltages and grounds were, and it was a little convoluted, like I said. So I think I'm going to rearrange the J7 header a little bit just to make it more intuitive to hook up. But if you do follow these pin numbers right here and just connect it like it says, it will work. That's what I did, and it's fine. So the VBAT and VBus is just connected to the board's VBAT and VBus. So VBAT comes from the positive terminal of the battery, and VBus is a 5-volt supply if you want to use an external 5-volt supply, like one that comes off of a battery charge breakout board. It will boost the voltage for you. You can just input that there. If you do that, you do not have to place a jumper on the 3.3 volt to VCC jumper. What that jumper does is it connects the 3.3 volt output from the microcontroller to the VCC of the rest of the board, and so everything's powered off of the microcontroller, the onboard voltage regulator of the microcontroller, which the hardware on the board right now is not going to pull anywhere close to the limit of the board, so you'll be fine. But like I said, if you want to use an external power supply, which I would probably recommend if you are powering more power hungry sensors, then you can do that. And that'll go through the LD1117 regulator to drop it down to 3.3. This C3 and R14 is for pulling current from an external supply if you need a trigger to enable the 5 volts. A lot of chargers will not provide power to the 5-volt rail if it doesn't sense a current draw or a voltage difference. So this is just to provide that initial draw and voltage difference. And I don't even use R14. I just included that in case I needed to use it. But usually I'll put like, I don't remember the board I used, but it needed a voltage difference. And so I would put a 20 microfarad capacitor there that provided enough pull to get it started. And then it would just stay on until you turn the circuit off. Start switch, I don't remember why I wired it up like this, to be honest, but it basically pulls the start signal low when it's closed, and it is high when you don't want it to be recording data. So when you flip the start switch, it'll start recording data, and then when you flip it back, it'll stop recording the data. And you can use, well, actually you need a toggle switch for this. It isn't a momentary switch, so it will keep reading until it senses that that start switch has been flipped back. That can be changed in programming. That's just the way I prefer to do it. And on the board, this is the start switch right here. So you flip it up and it starts running, and then you flip it back down and it'll stop, write the file, and then make it available on the SD card. So future changes that I want to do is to use an ADC instead of just the analog inputs right to the microcontroller. I want to use something that has a bit higher resolution and something that's kind of has a separate circuit for the analog inputs. But these are some changes that I already have planned as far as the main board components and the circuitry. Okay, so the peripheral hardware and connector description. Right now I'm using a 0.96 I2C OLED screen, very common component. You can see it right here. It reads off all the data that you want. You can configure it obviously with programming to display however you need, but I'll show you what I have selected and chosen to display on it here in a second. And you can see right here I've used IDC connectors to connect all the peripheral hardware. I just used that because that was easier to, crimp together than making DuPont connectors and doing each crimp individually. I just don't like having to do that. So IDC connectors work really well with a ribbon cable that you just split off and solder the wires wherever you need to go. It's very convenient in my opinion. For the inputs on J6, which is your analog and digital inputs, you can see down here I've used 2mm banana jack connectors. Those are kind of specialized and there's not a lot of probes out there that use those. So right now you kind of have to build your own probes, which sucks. I've already ordered B and C connectors, so like the same kind as your oscilloscope. So you can just use probes that you can order from Amazon instead of having to build your own. That's going to be on the next version of the hardware side, the peripheral hardware side. The J7, as I described earlier, you got your VBAT switch, the V-bus switch, the battery connection, which just goes to the positive and negative terminals on your battery, and you have to use a lithium ion or a lithium polymer to utilize the onboard charging circuitry on the M0 or 32U4 Datalogger. If you want to use a different chemistry, you have to come up with a different charging solution and connect that separately. If I wasn't clear, the 5-volt connection actually connects to the 5-volt. The V-bus switch connects the V-bus net on the board to the, I think it's just called V-bus on the controller as well. So that connects the 5 volts that's supplied to the board already to the board. The 5-volt connection actually connects the board to the 5-volt pin or connection on whatever external supply you're using. So those are two different ones. That kind of tripped me up when I went back to build the board. I was like, wait, why is there two of them? The battery, admittedly, I way oversized it. It's back here, but it's a 21700 4500 milliamp hour cell. It's made by LG, I believe, and it is way oversized for this purpose. The switches, I just used double pole single throws. I got a pack of them, so I connected the VBAT and VBus together on one switch in parallel, so those are connected at the same time, because I'm not using VBus because I don't have a external 5-volt power supply. But if you want to use either one, you can use both of them and just run those separately by not connecting the 3.3 to VCC jumper. And you have to leave that disconnected if you're using both, or if you want to use both of them. The sample rate potentiometer, you can see it right over here. Right now it's just a regular trim potentiometer, single rotation. I would recommend using at least 2 turns, just so you have a little bit more precise control, but you can use single turn or whatever kind of potentiometer you want, as long as it gives you a voltage division. Like I already said before, one of the potential changes that I would like to do is swap out the banana connectors for BNC connectors, allow standard oscilloscope probes to be used. You don't have to make your own. And then I'll probably decrease the size of this 21700 cell. It is probably 60% of the weight of this whole thing. Not that I'm really concerned about weight, it's still pretty light, but the 21700 is just way oversized. It's just what I had on hand. So I'll probably switch to one of the flat square cells that's probably like an 800 milliamp hours or something. Even that's probably bigger than I need to make it. But those are the only peripheral hardware changes that I have in mind right now. I was thinking earlier today about adding circular connectors with an I2C connection, which will allow you to attach other sensors that are I2C instead of just like digital analog input. It'll let you data log from I2C sensors. I'll probably include a one-wire sensor plug, so you can plug in like DS18B20 temperature sensors and other one-wire sensors. I think that would be really useful, and it'll probably be something I would even use regularly. So I think that would be a good addition. And then this is just the supporting documentation that is also in the package. When you download the zip file from my website, these files will also be included. So you'll have the datasheet for the 3.3 volt voltage regulator. You'll have the datasheet for the LM, that shouldn't say 193, it should say 393. But you'll have the datasheet for the LM393, the M0 Datalogger. I downloaded the PDF version of the full Adafruit tutorial for it, so you'll have the whole guide for all the ins and outs and tutorials for that board. You'll have the schematic for the Debugger Buddy, which is the actual PCB schematic, so you'll be able to see all the connections and how that works together. And then you'll also have the circuit layout for the board, so you can see where all the traces go and how they connect. And then last but not least, the working script v1. That is how I have configured the board and the readout and all that stuff the way I wanted. Again, this is completely changeable. It's up to you. You can do whatever you want. But I've included this just as like kind of a baseline to get you started. Okay, now let's look at the board actually functioning. Plug in the M0 Datalogger again. And I'm gonna focus on the screen because I think that's the most important part, but you turn it on. Say initialize SD. Says it creates a file. It shows the next file number, so it just creates a file called datlog, and then a number, which is the next in the sequence of however many files you have on the chip. I think I have it set up to be able to create like 99 files before it glitches out, so don't go Y2K on it. You can see the floating analog values right here. That's the result of the R2 resistor being too high a value. Like I was saying earlier, it's a 60K. It probably should be 10K, and then changing the R1 value to adjust for whatever you want that input voltage to be, or the output voltage from the divider. And then down at the bottom, you have the frequency, so you can program that frequency to change however you want when you turn that sample rate potentiometer. So you can go all the way up to 1023. I think I just have it on a 1:1 ratio. So there you go. And then it displays the current battery voltage up in the top right hand corner. So it shows the next file, battery voltage, your analog and digital input readings, and then your current sampling rate. So then if you want to start recording, you just flip the start switch. It's recording. It shows the file that it's writing to, and then whenever you stop recording, it gives you a little report. File created, datlog23, creating new file, datlog24, boom. And then it shows up in the top left hand corner, your next file is 24. So whatever you start recording next will go to datlog24, and 25, 26, 27, and so on. And since we are using the onboard charging circuitry on the M0, if you want, you can just hot plug in a supply. It won't interrupt anything, and you can just run it off like a battery bank or your computer or whatever you want, and it'll charge the battery while you're using it. You don't have to disconnect anything or flip any switches. One one behavior is that if you turn it off and you plug in a power supply source to the USB on the M0, since it's power supply going right into the M0, it will basically just turn on the circuit and display what you saw. Since you're turning off the battery supply to the M0 whenever you flip this switch, whenever you plug in a USB power supply, it will just turn on because there's nothing to turn off the board if there's power going to it through the USB. It goes right to VBus, the 5 volts does, and then you get the 3.3 volt out. If you have that jumper 3.3 to VCC disconnected, then the board will be powered, but it will not be able to communicate with any of the other circuitry on the board because it's not getting the 3.3 volts from the separate VCC net coming from the 3.3 volt regulator. So I hope that wasn't too confusing. I know that was a lot to go over in a short amount of time, relatively short, but I just wanted to give a quick outline and introduction to this tool that I made. It's completely open source. Feel free to download the package, do whatever you want with it. It is something that I'll be continuously updating. Like I said, I already have future plans for changes that I want to make to it, and I'm hoping that this will become a super useful tool, super handy and convenient to use. So if you have any suggestions of things that you think would be useful to add without adding to the complexity too much, because I would like to keep this a relatively simple tool, easy for advanced beginners, early intermediate makers to build. Please send me an email. My email is on this document. You can just shoot the suggestions there. Put them in the comment section of this video. Whatever floats your boat, visit my website. Use the contact me form there. But anyway, thank you guys for watching. I hope you guys enjoyed this. I hope you'll find it useful. Be sure to be kind to someone today, and I will see you next time. Peace. Here it just has the hey, Archie. Hey. That's okay. Oh boy. Come on. Come on. Good boy. Okay.